Thanks. And we are moving to the next talk, which will be delivered in, live. And it's to be given by Professor Federico Capasso from Harvard. Of course, Federico is one of those few who doesn't need really much introduction. But still, I'd like to remind maybe for some younger people, his truly remarkable contribution, starting, for example, from band engineering in semiconductor nanostructures, which is now so much in the heart of so many activities in photonics, that of course enable things like quantum cascade lasers, exceptionally important development, which allowed to cover the mid-infrared spectral range and enable sensing and many other applications. And of course, Federico is also known for studying QED forces, including first demonstration of repulsive Casimir force. And of course, most lately and most related to this conference, his outstanding work pioneering truly seminal work on flat optics enabled by metasurfaces. So we're all looking forward, Federico, for your presentation. I see you already sharing the screen. So you have the floor.
Yeah. Can you hear me?
Yes, we can.
Okay, great. Vlad, thank you very much for the introduction. And so what I'm going to cover here is work done in my group in the last, I would say, 3-4 years, okay? And I've entitled it Structuring Light and Dark with Metaoptics. And of course, you all know about structuring light, okay? You can locally control, you know, the amplitude, the phase, and the polarization. You get very interesting pattern. And this, in fact, goes back to the pioneering work of such luminaries in the field as Michael Berry, Miles Paget, and so forth. What we have looked lately is at singularity. Can we structure the actual dark by engineering special singularities? So this is really the second part of my talk. Here you have the outline. So without any further delay, let me go to the next slide. And you all know this, but in the interest of just giving a summary, let me see if I can actually use the pointer. Just hold on a second here. Okay. Spotlight, good. Ah, yes, that's nice. So you all know about spin angular momentum, which relates to the Eigen polarization, circularly and right circular and left circularly polarized light, which means a spin. These state correspond to +1 and -1 spin. You of course know about the optical angular momentum, the optical vortices. Here, the key quantum number is the number of twists that the wavefront does within a natural wavelength. So you have L equal 1. It forms an infinite basis, and that's why it's interesting for things more and more so for communication and so forth. So the key thought, there is a helical phase with this phase front here, and is a spiraling really of the Poynting vector along the propagation direction. Now, and I want to stress, for actually paraxial beam, and you know, paraxial beam is the actual domain of Fourier optics. You can actually write if you are in a state like this here, the total angular momentum being just the sum of the spin and the L quantum number. And now, why metasurfaces are important? Well, because they allow you to locally engineer not only the phase and the amplitude, but also the actual polarization. And that's a very important point here. And this goes back to a number of papers, the earliest one being from the Hasman group and so forth. And later there are contributions by my group, by the group of Faraon at Caltech and so forth. And the idea here is we can use structural birefringence, okay, to engineer. In this case, these are simply linearly birefringence elements here. And so you can impart along, for example, this direction X or Y, different phases here. And this can be described by a Jones matrix. Now, the actual phi and phi Y depend on the actual position here. So each has its own different Jones matrix. So at the end, and this is the cool stuff, you can see that how you can locally engineer essentially immediately after the actual metasurface, the actual polarization. You can use both the propagation phase by altering these dimensions here for a fixed height, but also change the orientation, and that's the so-called Berry phase. So I want to go first to some of the earlier work, and this actually started with the work on so-called Q plates by the Marucci group, this paper here. And we were inspired by this paper by saying, can we do the same thing, probably in a more controlled way technologically and also with more options, simply because the actual spatial control that you can use with these metasurfaces, these are our process based on titanium dioxide, allows you really to go to the nanometer scale, so you can have very well-defined singularities. So here to the left, you see the concept of these actually Q plates. Essentially what it is they're engineered a half wavelength plate. So at the design wavelengths, and in our case, that's actually green, okay, if you hit it with one spin, left circularly polarized light, what do you get at the output? You actually get the opposite circular polarization, but you see, this is a typical vortex phase here that you can engineer. This is in the case Q equal 1, and this is Q is a so-called topological charge, okay? So now what you can do is you can arrange an actual map here, and this is done typically in this case here by having fins that are exactly the same, they're halfway plate, but the orientation angle changes as you change the azimuthal angle phi, right? So you have this mapping here that alpha relates to this. This is the way you actually do it. Okay, so you now see that if you can plug this in here, and I've already done it, you will get at the output an actual optical vortex here in this case, it's designed for L equal actually 2. Now, if you hit it with the complement, with the opposite polarization, you find that you get a vortex that spins in the opposite direction here. So a key thing here that you are really fixed to conjugate values. Okay, if you again use a perpendicular incident polarization, you can design this, in fact, for a number of different bases. I'll go into that later. You get the conjugate state. This is our structure. This shows the results, both the intensity for L equal 1 and the interferogram. L equal 1 means you have only one spiral arm, L equal 2, 2, and so forth. Interesting, you can do more interesting stuff that goes back to the pioneering work of Michael Berry and actually Ni. They wrote a beautiful book on singular optics. Okay, you can engineer also so-called structure which have a fractional orbital angular momentum. And then what you get, you get dislocation lines that you can see very interesting in the interferogram here. So we have tried to generalize this way, and this is done in a pretty powerful way, and this is in this paper here. So the idea now in the J plate is to overcome the constraint that as you go to the perpendicular incident polarization, you actually get only, you get the same orbital angular momentum with the opposite sign. So you get conjugate state. So here we have engineered this with this mapping shown here, and we call them J plate because really you are controlling the total angular momentum, right? Not only vortex orbital angular momentum plus spin. So in this case here, this is for an arbitrary elliptical polarization. You will get for this polarization, this vortex here with this quantum number. If you hit it with a perpendicular one, that's what you get, okay? And the way, what you can actually show, in general, it's not easy to find an analytical solution, but if this basis is actually circularly polarized light, you can write some very nice formulas for the J plates here. And this gives you the analytical solution of for the required phase shifts and orientation angles. Okay, this defines completely the local structurally birefringent meta atom, if you wish. This shows a micrograph, and this shows the actual layout. And So I'm just going to give you one example, but it's kind of cool to show this is an actual, we have used, chosen here two different optical angular momenta, a vortex of 3 and n equal actually 6. And the designer polarizations in this case are circular right and circular left. Okay, so what happens is, see, let me show you here. If you now hit it, with this one polarization like R, what you get is the vortex plus 3 here, which is a small vortex here. You see, this is the I state. This is a Poincare sphere. If you now hit it with the opposite polarization, left, you see the actual larger vortex 6. These ondulations are because we have made no effort to control the actual radial quantum number of the actual vortex. But in principle, that can be done. Okay. Now, what happens is what you can hit it now is with a superposition of your polarization. So you can move now, for example, on the Poincare sphere along the equatorial plane around this trajectory here. And you see very interesting things. You see, as I move along, you notice is, first of all, this is intensity. There is a number of singularities. So the reason is the following. Okay, the number of singularities that the extra vortices where I'm pointing here is simply, it can be shown to be the difference between n and actually m. Okay. So you see, you move along this state, and so you get very interesting structural light, and you see the extra singularities here in the fact that you see these branching here of the interferogram. So it's a way to engineer very interesting structural light state. Now, this work attracted the interest of Andrew Forbes, who has done a lot of pioneering work on various aspects of quantum optics, and he approached me and said, Federico, why don't we place one of your, we try to get high optical angular momentum lasing. So the idea is this: you place a J plate here, okay, and then you can actually rotate the actual J plate here. This is a two cavity, okay? Let me describe this cavity here. This is a second harmonic generation lasing. The actual second harmonic light is created. This is the cavity here, okay, by this crystal here that is within the near IR cavity of the 106 micron pump beam. So you really get second harmonic generation lasing here. And with the J plate, you can actually control the polarization. Now here, I want to give credit to terrific postdoc I had for a number of years. This is really an incredibly hard metasurface to make because you really have to go at the absolute nanoscale here. And this is a metasurface where the two polarizations that we're interested in are horizontal and actual vertical. What does this sign mean? If you hit it with horizontal polarization, you will laze on a optical angular momentum of 10. When you hit it with the vertical polarization is much larger. So we want to have really this changer to see what is the highest state that we can actually laze at. And this is in this paper here. So let me see. Okay, sorry about this. Sorry about a little. Okay, this is shown here to the right. Okay, these are the actual data. Now you have to turn your head here because the north pole of the Poincare sphere is actually here. So this is a circularly polarized state here. So you can see now that if you hit it with a combination of your Eigen polarization of these, let me call these Eigen, these are actually product states, okay, with a linear combination of these, okay, as you change the mixing. And how do you change the mixing? By simply rotating the actual J plate. So you can see here, as I'm rotating this, I'm actually moving along the equatorial plane, and I generate, in this case here is the pure lasing at 10, and here the pure lasing at actually 100. Okay, so Actually, the radial polarization here will actually well controlled. So it's quite exciting, and I see a lot of opportunities in the future for J plates, for actually quantum optics, quantum electronics. I now want to move to the recent work of my group. We've been asking the following question here. Can we design essentially spatially a metasurface that produces beams with spatially varying optical spin angular momentum and optical angular momentum, and actually a combination of both as we move along. So can I engineer, for example, a situation with a single metasurface? Essentially, I create a virtual polarizer here where the virtual axis rotates. And so if I now measure the intensity here, I will see that we'll be progressively going from maximum to minimum and so forth. Same for the optical angular momentum. Now, this is what we call is a 3D J plate, because we do not only structure light along the transverse plane, but along the Z propagation. So in this case, what happens, for example, for this particular designer polarization, I will have an evolution of the vortex from a small value to a larger value here. And here, instead, for the perpendicular polarization, I will see a different behavior. I will actually go from a different orbital angular momentum. It will be a different evolution of the orbital angular momentum between the state here and the state here. And this can be designed. Finally, I can have my cake and sort of eat it by combining this with this. Now, here I want to bring up a point that so that I want to clarify it immediately. Now, you know that, say, you are in free space, spin and optical angular momentum must be conserved. True. These effects here, they occur paraxially, near the center of the actual beam, which means that in every point, if you integrate, in this case, the spin angular momentum densities along the transverse plane, everywhere, it is completely conserved. You can verify, of course, by simulations, that's trivially, but also experimentally. Same is with the optical angular momentum, it is conserved. So what happens is, what does this mean? It means that locally, you have a redistribution of actually light, so that indeed locally you evolve from one optical momentum to the other. And then you, because of total optical angular momentum conservation, in this case spin, and this okay, there is a distribution of light away from the axis, so you still conserve things. So physics is actually holds, which is always good. Okay, so this is the qualitative thing. So how do we do it? Well, so this is what we need to do. The key idea is this: to produce Bessel-like beams that propagate for long distance while overcoming diffraction. And the work is actually described in this paper earlier this year. In fact, so that's what we want to read. Now I design a polarizer where you rotate the axis or a wave plate. I'm just going to limit myself to show the polarizer. And so what's the idea here? Look, it's very simple. Sorry about this. So what do we want to do here? We want to create a metasurface, it's right on the edge side, that implements a superposition, I worded this very carefully, of pencil-like Bessel beam with different KZ, which means different cone angle. So you really have a comb in reciprocal space, where KZ, these angles in array optics, probably you can call different Bessel beams here with different KZ. Okay, and then what you do is you have a spatial beatings, okay, and you get a spatial beating of this pencil-like beam with different KZ and polarization states. And so what you get, this evolution of the polarization axis as you move along the surface. Here, I really do not have a lot of time, but it was designed with a paper with that we published a few years ago, which is a powerful generalization of Fourier optics, which we called matrix Fourier optics. So it's a Fourier series of spatial harmonics weighted by different Jones matrices, which produce a spatially varying Jones matrix. Okay. So again, the device implements a superposition of Bessel function with slightly different spatial harmonics that form an actual comb equally separated in K-space. Now, and each Bessel function, this is important, is in this superposition, right? It's a superposition here, the top equation here, is weighted by a different Jones matrix, which is obtained how? By this simple Fourier relationship here. So if you like, this gives the amplitude, but this amplitude is like an actual matrix because you want to change the polarization. So it takes a while to figure this out, but then, so that's what we did, rotating linearly polarizing. And the Metasurface implementation, I really need to go fast, is how we do a distribution. You see a polarizer, when we make a polarizer, we know that it's non-unitary. There is an amplitude modulation. So you cannot simply use just a single metasurface where you just have birefringence phase plates. That will not do the amplitude modulation. But there is a trick that we have used, and in fact, it's quite well known. It's a generalization of the Getu phase that was introduced by Lohmann at the beginning of computer-generated holograms. And so what we do is intuitively, I'm going to explain you, we interface different metasurfaces here that at the end, you get the modulation of the amplitude by interference of light produced. This is the best intuitive way I can explain this. Okay, and you can write, in fact, two different type of matrices and so forth, but I don't have time to go into the mathematical details. This is a fabricated device. The experimental setup, this is very general for what I'm going to talk about next. So what you have is a polarized and a halfway plate, so you can, of course, control the polarization here. Here's the actual metasurface here, okay? And what you do, you rotate the metasurface to change the different polarization response. So what you do is this, okay? Here, this is the Fourier plane here, okay? So what you do actually is this arrange the numerical aperture of this, that you actually produce a filtering effect. So you don't want to see all the actual structure here, right? Because that's due to a redistribution of actually light, okay? So this 4F system images and filters, so it's a K-space filter, if you wish, the response of the metasurface on a CCD camera. And then you have a Stokes analyzer there, and simply by doing an actual translation, what you can actually find out, you know, the distribution, this is a Z-plane, of the polarization along the Z-axis. And this is the simplest example. For XInput polarization, you see a distance which is significant. It's a few millimeters. We could do longer, of course. It's basically related, you know, how can you make your Bessel beam as close as to diffractionless? The more so you can extend your distance. As you move along here you get maximum intensity. The virtual polarizer, it's almost lined up with the XInput polarization. Then it's rotated, it dims it, you go to 0 and so forth. And then for the input polarization, you do the opposite. We did this also for a wave plates, of course. And so the 3DJ plate, again, we want to make a switchable device that can generate two arbitrary set of 3D vortices, again, not only in the XY plane, but along the propagation direction also, okay? And so that the optical angular momentum changes. Then we want to demonstrate also a total angular momentum plate that generates revoltas in which not only the topological charge, but the polarization evolves. Now, I want to insist this transition occurs only locally at the center of the beam. The global total angular momentum is, of course, conserved. Okay, and this is what our plan, what we have done. This is a 3DG plate. Again, for one polarization, you evolve from this vortex to the other. For this, and you can really choose different vortices depends entirely on the design of this. So you can really structure light along the z direction, in a sense, three-dimensionally, but locally, as I did before. So here what you want to do, well, what you want to create now here is actually two combs, okay? One comb that actually optical angular momentum modes separated in actually scale space. So they're actually spatial frequency combs here, okay? And this is one comb, this is the other comb. This relates to one optical angular momentum, this to the other. Now, what you show, this is actually the actual simulations here, that you can see that intensity distribution will evolve along the propagation distance, being a vortex at one end, being a vortex at the other, and then a superposition. And again, it's all based on playing with interference. So this works well because the energies disperse into the outer rings, actually, so that locally, paraxially, if you wish, you get this very nice behavior. This paper will appear soon in Nature.com. This is a fabricated device. It's kind of fascinating to see these pictures. And so now let's see if I can run the movie here. For this polarization here, I think it's circular. Yes, I now hit it here. You see the movie. This is now, I'm moving the actual, I'm translating thing along the z-axis. So I see the evolving intensity profile from L = 1 to -3. In this one, in case I do actually, I hit it with this, with the other state, okay? And that's what you actually get. You get a transition from this. So it's correct to call this a 3D J-plate. And let's say what I have next here. Well, sorry, folks. Oh dear, I'm having problems here. What's going on? Okay, this is the 3D J-plate designed for elliptical Eigen polarization. Again, this now shows the different snapshots here. You see, if you hit it with one elliptical Eigen polarization, you see the evolutionary space from this vortex here to here. As I said before, I just showed the movie. This shows actually when you hit it with the perpendicular ellipsis, if you wish. This one here, these are the two input ellipses. And then you can hit it, of course, with a superposition state, and you get very complex structural light along the axis. So it works out very cool from both a simulation and you can see here, and the experiment. Look, the agreement is indeed excellent. And this goes credit a lot to the incredible skills of fabrication. Some of my people here, we did sort of the icing on the cake to engineer. We can control now both OAM and SAM along the propagation axis. So now I want to tell you about this work, and this is actually, it's going to take me just a few minutes to finish here. So let's talk about singularities in general. I have a complex scalar field with a real and an imaginary part. And what does it mean actually to have a singularity? Well, it means that the phase singularity is undetermined, is undefined, and you can define which region of space. It could be 0D, it could be a vortex, linear, or in our case, can we engineer a surface which is singular? So we have to arrange this. And of course, the intensity is actually 0. And a lot of pioneering work again here by the people that I said about singularities. Now, I'm going to say just a glimpse on the actual method. You could minimize the field amplitude, but we have decided to maximize the phase gradient. Well, it's a natural matrix. It is agnostic to the amplitude scale. And what essentially you maximize the phase gradient locally. So you really do is you are align these zero surfaces, the zero surface, the imaginary and the real part. And you can essentially go asymptotically very close, of course, to the actual singularity. So you maximize the phase gradient orthogonal to the design sheet. And I want to show you this because it's really cool. This should really give a major credit to my great graduate student, Daniel Lim. And the idea, so this is a setup here. You see, I have, of course, the Metasurface, and I'll show you this later. Okay, and we want to design a heart-shaped singularity, literally. And which means what a heart-shaped singularity? Well, maybe I should actually have gone to this. This is a singularity region. Now, what we do as we do this translation with our setup, we actually look at this intersection. Of course, we would like to be ideally paraxially, but it's very hard. So it's actually, after a distance, become unstable, the singularity, but the effect is actually very clear, and I can show it here. Okay, you see, I'm now translating. Look at Z, very clear heart shape. This is a simulation, so the agreement is actually reasonably good, I would say. And this is the experimental phase and the simulated phase. Okay, so and this is essentially what we have actually done. Okay, we have used again our recipe of titanium dioxide nanopillars in the green, and you can see here the device map. Again, the isosurface. And finally, I want to address the point of the topological charge of a two singularity. We know the topological charge is contouring is invariant under small field perturbation. Okay, now how about 2D singularities? How can we think about it? For our case in particular, with close cross section. This is not a heart, but you get my point, right? This is a singularity cross section here. Okay, if you like to, the way you have to think of this contour integral, you know, you have to, when you do the contour, you needs to be split in two curves to exclude the contribution of the two regions. So when you do this contour integral along the dashed line, you see things cancel out here. So you get two paths with the opposite sign. So basically what you have, the topological charge is actually zero. I am careful in saying this is for our particular case of 2D singularity, but this sort of puts it in the general context of topology. So the applications, there can be many. I know that I am basically run out of time, but we want to make new kind of traps. We want to think again at what Stefan Hell did, because you can structure in the dark is a very powerful concept. You are not limited by the diffraction. I want to acknowledge my great collaborators, Ahmed Dorais, a postdoc, Daniel Lim, really in charge of the singularity work, and others here, and the contribution. And last but not least, great collaboration that I had with my friend Andrew Fobe and his team at University of Witwatersrand in South Africa on the high OM laser. Thank you for your attention.
Thank you very much, Federico. Quite a journey, lots of exciting recent results. So you're going from engineering band structure to engineering optical singularities, quite impressive. You took this to a new dimension, romantic dimension, by engineering this heart-like structure. That's amazing.
Well, I wanted something else, but you know, I said, this sounds cheesy. And he said, no, it's not cheesy. It's good. And I said, okay, you have done the work, so let's go with the actual heart.
Yeah, that's cool. That's cool. Any questions you could raise hands, folks, or send it through Q&A session. I don't see it right away. I guess people are overwhelmed with lots of information. Maybe I ask a kind of generic question. I guess by now, no one would have any doubts that this Metasurface-based flat optics is going to have tremendous impact on industry technology. It's happening right now. But let me ask you what scientific challenges you see in the field, which potentially also perhaps could open yet other new technologies.
Well, you know, this is an actual deep question. recently I've been fascinated about topology because, you know, of course, they gave a Nobel Prize for topology and so forth. There have been a lot of attempts to design interesting topological devices. There's been some, for example, some beautiful work on topological laser. I'm just singling one out. It's been by several groups. One is by Boubacar Kanté at Berkeley, also by Christo Dulides down at Central Florida. Now, of course, I'm always interested in asking the question, among all the phenomena, can we find the ones that are robust to technology changes, fluctuations, so that when they can be utilized? I would say metasurfaces, I think we agree, are having this impact. I can just tell you something, that our startup company that now is really gone into a situation, MetaLens, where we are working with a major foundry to produce metasurfaces with 10,000 metalenses, and these for dot projectors, and in the future they'll be using cell phones. So this is now fine, but this is sort of trying to do much better than what is there, you know, with metasurface technology. The question, can we create new functionalities with topologies to create something sort of the brilliant solution for an actual problem? I wish I knew the answer, but that's where I want to sort of, Vlad, tailor my search in the near future, because it's right, this sweet spot where excellent science in principle in the future can meet kind of new technology. I wish I had the answer, but I'm stimulating my group to spend precise in this direction. And I believe it is actually going to happen. It's only a matter of time.
So this is fascinating indeed. There are a couple questions came up. One from Thomas Clark. Is there any trick to make the full width half depth less than diffraction limit?
No, for the singularities, we are, of course, below the diffraction limit. So you must be thinking about now structured light, right? For structured light, yes, it relates all to how well defined you can do these nanostructures. And we definitely are at the diffraction limit there. We saw it in our early MetaLens work, simply because these fins can be controlled so well. And when I say the vertical, the height, they're perfectly vertical. That's true within plus or minus one degree, okay? Now, laterally, of course, you have fluctuation here, but as long as it's not a systematic error, there is an averaging effect. Also, remember also that the optical wavelengths is much larger than the sizes here. So it's much more forgiving, making these metasurfaces at the diffraction limit for structural light than it is to make the IC, the latest IC nodes, which are nanometer, because there you are fighting against the electron wavelengths, which is not 1,000 to 2,000 angstrom, you see. So the advantage, there is this advantage of metasurface. You're working on optical wavelengths, right?
Yeah. Okay, one more question, probably the final one, because we're running out of time, by Ginal. And well, let me read it, Federico. Thanks for the illuminating talk. Phase singularities are observed even at lasing threshold in parameter space, not the special space as described here. Can you please let us know where the parameter phase singularities can find applications?
Well, parameter, well, let me say, every singularity, essentially, let me define the most trivial singularity. It's not trivial. It took a while us to figure it out. Of course, this is not a discovery. The longitude is a natural, becomes a singularity when you go to the actual North Pole, because you cannot define the longitudinal, the source poles, wherever you have a parameter. So we did also, I didn't have time to talk about it, to realize polarization singularities. where essentially what is the parameter that becomes singular? It's the azimuthal angle. And we have actually beautiful pictures there. So we can definitely choose a number of parameters. We choose phase and polarization. There can be also now what you raise about lasing. This is now fascinating because, by the way, now you can, it gets very, very interesting. I'm starting to think in this direction. When you start to laze, now, is this robust about lasing? I would say yes and no. It all depends if the nonlinearity of the material at some point doesn't take over, and it takes over, for example, in some of the beautiful work that the chairman did with Bob Boyd, or in actual parallel, where you're losing the nonlinearities. There, the nonlinearities can influence the singularity, or maybe we can ask the question, can we use the nonlinearity either to treat it a kind of an enemy that can destroy the singularity at high intensity, as actually helps to trigger a singularity so that a certain intensity, bingo, this singularity shows up? I mean, I think this is a very good question. Thanks for asking this illuminating question.
Well, thank you so much, Federica. As always, very visionary, inspiring talks and lots of recent developments. Let me close this plenary session and thank everyone participating. And we hope that the rest of the conference will be as successful as this session. Thank you so much. Bye, guys.
Thank you.